Close your eyes and imagine nothingness. Not a dark, empty space, because space is something. Not an extended silence, because time is also something. Try to imagine the absolute absence of dimensions, of matter, of physical rules. It is impossible for the human brain to conceive true nothingness, because we have been shaped by the rules of something. However, 13.8 billion years ago, the entire vastness of our observable universe, with its trillions of galaxies and countless stars, did not exist. All matter, all energy, all space, and all time that would one day exist were crushed into an infinitesimally small point. A point with no volume, but with infinite density and heat. Physicists call this singularity. Within this inconceivable grain, the laws of physics as we know them completely lose their meaning. Gravity, electromagnetism, and nuclear forces are fused into a single, indescribable primordial force. And then, the zero moment. The limit of our knowledge and the beginning of everything we are. There was no bang because there was no air to carry the sound. It was not an explosion expanding within space, but space itself exploding and unfolding out of itself. In a microscopic fraction of a second, the universe's clock began to tick. The Big Bang was born. What happened next challenges intuition. During a period called cosmic inflation, which lasted a trillionth of a trillionth of a trillionth of a second, the very fabric of space expanded at an incomprehensibly faster speed than the speed of light. The universe went from the size of a subatomic particle to the dimensions of an apple, and shortly after, to the size of our current solar system, stretching tiny quantum fluctuations to gigantic scales. The newly born space is a chaotic hell. The temperature is in the billions of degrees. There are no atoms. The heat is so extreme that subatomic particles cannot come together. The universe is filled with a boiling soup, a hyperdense plasma of quarks and gluons, the fundamental building blocks of matter, colliding and annihilating frantically in an ocean of pure energy and blinding light. As space continues to expand brutally, this expansion forces the universe to cool down. The energy, stretched by the growing space, begins to lose intensity. And it is here that Albert Einstein's most famous equation, E equals mc squared, takes center stage in the cosmic arena. The cooling allows primordial energy to start condensing, freezing into solid particles of mass. Matter is being born from light, but this birth is a war. For every particle of matter created from energy, an identical particle of antimatter is born as well. They are like reflections in a mirror, opposite in charge. And when matter and antimatter meet, they annihilate each other instantly, returning to pure energy. During the first moments of the universe, trillions of these annihilation battles occurred every second, threatening to return the universe to emptiness. The fate of our existence depended on a mathematical imperfection, a rounding error in the laws of physics. For a reason that modern science still struggles to decipher, an asymmetry occurred. For every billion particles of antimatter, the universe created 1,000,000,001 particles of ordinary matter. When the Great Annihilation War ended, only that one left over remained. Think about the magnitude of this. Absolutely everything you see around you today. The mountains, the oceans, the distant galaxies, the cell phone in your hand, and the physical body that houses your mind. All of this is made from the remnants of that primordial asymmetry. We are the statistical residue of an invisible cosmic war that occurred in the first milliseconds of creation. A second has passed since the Big Bang. The temperature has dropped to only 10 billion degrees. The plasma has cooled enough for the strong nuclear force to come into play. The quarks, which had been wandering freely until then, are captured and grouped into threes, locked in an inseparable dance. The first protons and neutrons are born. The heavy structure of our material world has been forged. 3 minutes. The universe enters the era of nucleosynthesis. The heat is still extreme enough to act like the interior of a star. Protons and neutrons collide violently and begin to stick to each other. In a frantic window of just 15 minutes, the first stable atomic nuclei are created. 75% hydrogen and 25% helium. This ratio dictates the chemistry of the cosmos to this day. Despite having atomic nuclei, the universe is still not ready for light. For the next 380,000 years, it continues to expand. The scene is a colossal storm of hydrogen nuclei and free-floating electrons. As the electrons are free, any photon of light trying to travel through space collides with them almost instantly. The entire universe is an opaque, dense, and overheated fog where light is trapped. Until then, in the span of 380,000 years, the universe reaches a critical turning point. The average temperature drops to 3,000 degrees Celsius. The heat is no longer sufficient to keep the electrons loose and frantic. Electromagnetic attraction prevails. In a cascade that sweeps across the entire cosmos at once, hydrogen nuclei capture the electrons, pulling them into stable orbits. With the electrons now trapped in newly formed atoms, the empty space finally emerges. The mist dissipates. For the first time in the history of existence, the photons of light gain a clear path. They shoot off in all directions, traveling through the vacuum uninterruptedly. The universe becomes transparent. The first flash of light occurred, bathing the entire cosmos from one end to the other. This first light of creation has never disappeared. As it traveled for 13 billion years, the expansion of space stretched the light waves, transforming them from visible brightness to microwave radiation invisible to the human eye. We call this cosmic background radiation. It is the thermal scar of the Big Bang, the baby picture of our universe that still surrounds the Earth on all sides, permeating the space between galaxies. The proof that this is real was literally in the room of your house. Before digital TV, when a tube television was not tuned to any channel, it displayed a black and white static noise. About 1% of that visual and sound static you saw on the screen was caused by ancient photons from the cosmic background radiation hitting your TV's antenna. You were watching the echo of the Big Bang in your living room. But after this initial flash, the primordial light weakened, swallowed by the expanding space. With no stars yet born to generate new light, the universe plunged into its darkest and loneliest era. Scientists call this long period the Cosmic Dark Age, a period of hundreds of millions of years of total darkness and absolute silence. Matter, in the form of cold clouds of neutral hydrogen, wandered through an ever-growing black void. It seemed that the universe had been born only to slowly freeze and die. However, hidden in the darkness, the patient architect of the cosmos began to work. Gravity. Remember those tiny quantum fluctuations that were stretched in the first millisecond? They caused hydrogen to be distributed slightly unevenly. Some areas were imperceptibly denser than others, and where there is more density, there is more gravitational attraction. Ordinary matter did not work alone. A ghostly substance that does not interact with light, dark matter, acted like the invisible scaffolding of the universe. The large pockets of dark matter formed enormous gravitational wells, slowly pulling the rivers of cold hydrogen gas toward their centers over silent ages. The attraction is slow but relentless. In the denser areas, trillions of tons of hydrogen gas begin to collapse under their own weight. The enormous mass accumulating at the center causes the gas molecules to collide with ferocity. Like a bicycle pump that heats up when you quickly push the air, the center of these colossal clouds begins to heat violently due to friction and the overwhelming pressure. The temperature in the cores of these dark clouds rises alarmingly. It goes from just a few degrees above absolute zero to thousands, and then to millions of degrees. The cold, inert gas of deep space has been compressed to transform into a state of incandescent plasma. The gravitational pressure in the core became so monstrous that it began to crush the very nuclei of hydrogen atoms. When the temperature reaches the critical 15 million degrees, the laws of atomic repulsion are defeated by the brute force of gravity. Protons are crushed together, fusing into helium in a gigantic thermonuclear reaction. The pure energy released by this fusion shoots outward, fighting against the weight of gravity. The core comes into balance. The darkness ends. Let there be light again. The ignition of the so-called Population 3 stars occurred. They were the first luminous objects in the universe. They were aberrations compared to our sun. Gigantic, made exclusively of pure hydrogen, 100 to 1,000 times more massive than our star, and shining with an unmatched blazing blue ferocity. Hundreds of millions of years after the Big Bang, these superstars begin to ignite, one by one throughout the fabric of the universe, illuminating the cosmic darkness like city lights emerging at dusk. The universe was awakening. Primordial hydrogen found its purpose, becoming the fuel that ignited the sky. The Dark Age was coming to an end. The universe now had engines of light and heat. However, these first massive stars were destined to live quickly and explode spectacularly. In the next part of our journey, we will see how the ashes of these first stars built supermassive black holes and paved the majestic cities of light that we call galaxies. The first stars of the universe reigned fiercely, but briefly. Because they were so colossally heavy, the gravitational pressure in their cores required them to burn their hydrogen nuclear fuel at a terrifying rate to avoid collapsing. While our little sun can burn for billions of years, the primordial giants consumed their life in just a few million years. The universe lit up quickly. When the fuel runs out, nuclear fusion stops. Without energy pushing outward, gravity wins in a fraction of a second. The star collapses in free fall, at a quarter of the speed of light, bouncing off the superdense core and violently exploding in a supernova. These explosions were crucial. It was the absurd energy of those first supernovae that forged the heavier elements than helium: carbon, oxygen, silicon. The chemical building blocks of life were cast into the abyss. But what happened to the crushed cores of those first stars? With so much mass compacted into such a small space, the core collapsed into a state of infinite density, tearing the fabric of space-time. The first black holes of the universe were born, dark, invisible spheres wandering among the clouds of gas. The black holes would not go hungry. Feeding on the vast ocean of hydrogen gas around them, these primordial black holes grew monstrously. They devoured entire stars and found themselves in the void. When two black holes collided and merged, they sent tremors so strong through the fabric of reality that we now know them as gravitational waves. Cosmic predators. In the center of enormous gas knots formed by dark matter, black holes reached unimaginable sizes, millions and soon billions of times the mass of the sun. Quasars were born. The surrounding material was spinning so fast that the friction heated it to absurd temperatures, emitting beams of energy brighter than trillions of stars combined, illuminating the cosmic vastness. Attracted by the formidable force of these supermassive black holes, billions of newly born stars began to cluster together. The universe started to organize itself into gigantic structures, galaxies. These immense whirlpools of light, rock, gas, and gravity became the independent islands where all subsequent chemistry of the universe would occur. And the scale of this construction was staggering. If we point the most powerful telescopes at a tiny square of the sky, we will see thousands of these galaxies clustered together. The universe was not creating tens, but about 2 trillion individual galaxies, each with hundreds of billions of stars. The scale annihilates human understanding. 13.6 billion years ago, the foundations of our own house began to come together. An irregular proto-galaxy started to accumulate mass, devouring neighboring dwarf galaxies through galactic cannibalism. This structure stabilized and rotated, forming the elegant, flattened disk with spiral arms that we now know as the Milky Way. In the pulsating heart of our young Milky Way, Sagittarius A star settled, a supermassive black hole that holds about 4 million times the mass of our Sun. At the beginning of our galaxy, he was a hungry monster that devoured the primordial gas and dust, precisely shaping the spiral structure that houses us in the galactic suburbs. The Milky Way became a factory of stars. In its spiral arms, gravity compressed rivers of gas, creating nebulae, the true stellar nurseries, clouds rich in heavy elements scattered by ancient supernovae. The new stars would inherit the chemical complexity of their ancestors. They would not be made up solely of hydrogen. As our galaxy stabilized its brightness, the universe continued its expansion. The galaxies are aligned like pearls along invisible filaments of dark matter, creating the cosmic web. Among these threads, there are deep voids, the largest deserts of nature, sterile bubbles of nothingness with hundreds of millions of light-years in diameter. The routine of the cosmos has been established. For billions of years, the life of stars followed a cyclical pattern. They were born in nebulae, burned their fire, and enriched the periodic table. When they died violently in supernovae, or slowly as white dwarfs, they returned this recycled material back to the dust clouds. The cycle continued. The universe was slowly changing its own constitution. With each generation of stars, less pure hydrogen remained, and more metals, carbon, nitrogen, and iron polluted the interstellar clouds. This metallic pollution was the best accident for us. In a universe of pure hydrogen, there would be no rock, there would be no water, and definitely there would be no biology. Billion after billion of years passed. The universe aged. The frenzied rate of star birth began to decline. Collisions became less frequent. The stage was set. About 9 billion years after the Big Bang, we will focus our attention no longer on the vastness, but on a calm corner. In the Orion Arm, far from the radiation of the galactic core, Ali floated a large and cold molecular cloud of dust and gas, waiting in the darkness. It contained the dead ashes of previous stars, rich in carbon, iron, ice, and silicates. Our nursery. For that cloud to transform, it needed a push. This disturbance came from outside. A nearby supernova sent a powerful shockwave tearing through space across the Orion Arm. When the wave hit the cloud, it compressed the gases. Gravity took control. The cloud collapsed and began to spin, faster and faster, folding into a gigantic disk. In the center of this disk, 99% of the mass was pulled to the middle. The crushing generated inconceivable heat. Hydrogen atoms began to fuse. The core ignited. The sun was born. Our sun encountered its first light, emitting solar wind that swept away the hydrogen around it. A yellow dwarf projected its rays. We were 4.6 billion years ago from today. The birth of the sun left a crucial remnant, the protoplanetary disk. A ring of debris that continued to orbit the star, like dust swirling on a cosmic racetrack. It was hot and cold. It was a process called accretion. Dust grains stuck to each other due to static electricity. They became gravel, rocks, and massive meteors tearing through orbits. Over millions of years, the race reached its climax. Giant bodies of molten rock crashed in daily apocalypses. Entire planets were forged by the kinetic heat of destruction. In the third ring, a survivor emerged. A melted sphere of boiling magma, bombarded by debris and solar radiation. It was day zero of our home. The Earth had taken its place. The stage for biology was set, but we still didn't have the blue planet. The Earth needed one last epic cataclysm to stabilize. Now we will witness the impact that created our moon. 4.5 billion years ago, Earth was not a home. It was an uninhabitable hell. Geologists call this era the Hadean Eon, a direct reference to Hades, the Greek underworld. Our newborn planet was a sphere of molten rock, spinning frantically in the dark vacuum. A day lasted only 6 hours. The sun, still young, shone at only 70% of its current intensity. But the surface of the Earth bubbled at thousands of degrees, illuminated by the terrifying glow of global oceans of magma. There was no air to breathe, only a thin and suffocating atmosphere composed of hydrogen and helium, which would soon be swept away by the violent solar winds. The bombardment of asteroids was constant and relentless. Immense debris from the formation of the solar system collided with the molten surface, merging with the planet and increasing its mass. Earth was a radioactive nightmare, a chaotic cauldron where the heaviest metals like iron and nickel slowly sank toward the center, creating the magnetic core that would one day protect us. But the inner solar system was still overcrowded. Gravity was still organizing the neighborhood, and the orbits were not fully stable. In the same orbit as Earth, another protoplanet formed, a world the size of Mars, which scientists today call Theia. For millions of years, Theia and Earth danced a deadly gravitational waltz around the sun, orbiting dangerously close to each other. It was a planetary-scale disaster waiting to happen, until the balance was broken. Attracted by the Earth's inescapable gravity, Theia left its position and accelerated toward our planet at an estimated speed of 40,000 kilometers per hour. The impact was not direct, but a devastating side collision. When the two worlds collided, the energy released was billions of times greater than the atomic bomb in Hiroshima. The Earth's crust was instantly vaporized. The mantle melted. Theia was annihilated, completely shattered into liquid rock and superheated gas. For a tragic moment, it seemed that the Earth would also be destroyed, exploding into a belt of asteroids. The collision deformed the planet into an almost unrecognizable oval shape. Billions of tons of smoking debris, the pulverized mantle of Theia mixed with the Earth's crust, were hurled into space at astronomical escape velocities. The Earth survived by a narrow margin, but gained an incandescent halo, a ring of swirling magma debris around it, very similar to Saturn's rings. In the chaotic orbit of this ring of destruction, gravity acted quickly. On a remarkably short timescale, perhaps just a few decades or centuries, the shards of molten rock began to collide, merge, and group together. The largest piece attracted the smaller ones. The fury of the impact was gradually replaced by the spherical order of physics. There, forged in the fire of Earth's near annihilation, our moon was born. Originally, it orbited 10 times closer than it does today, dominating the night sky. This primordial moon was a terrifying and magnificent object. If you were on the melted surface of the Earth at that time, you would see the moon occupying almost a third of the sky, shining intensely in red due to its own unmelted magma. But its presence was the greatest gift our planet has ever received. The gravitational pull of this colossal satellite began to act as a stabilizing anchor for our wounded world. The impact of Theia tilted the Earth's rotation axis by 23.5 degrees. Without the massive gravity of the moon to keep that axis stable, the Earth would wobble chaotically over the millennia. The poles would melt toward the equator and freeze again, creating a climate so unstable and violent that complex life would be impossible. The moon blocked our tilt, ensuring the regular and smooth cycle of the seasons we know today: spring, summer, autumn, and winter. The friction caused by the enormous gravitational tides of the moon, which at that time deformed not oceans of water, but oceans of solid rock, began to slow down the rotation of the Earth. The frantic 6-hour day was slowly stretched over eras. the planet finally began to calm down. The magma on the surface cooled enough to crystallize, forming a thin and dark basalt crust floating over the boiling mantle. The ground finally hardened, but the Earth was still not at peace. The pressure beneath this new, thin crust was unbearable. Thousands of volcanoes tore through the newly formed surface, expelling the trapped heat from the impact of Theia. These apocalyptic eruptions spewed not only lava but also enormous amounts of gases: carbon dioxide, nitrogen, ammonia, methane, and, crucially, water vapor, which had been trapped within the rocky minerals since the planet's initial formation. These gases expelled from the planet's depths were retained by Earth's gravity, forming our first secondary atmosphere. It was a toxic and suffocating chemical mixture, incredibly dense, which turned the sky reddish and prevented sunlight from penetrating to the surface. The water vapor expelled by the volcanoes rose, saturated the primitive atmosphere, and formed a global cover of uninterrupted storm clouds, kilometers above the scorching ground. And then, the outer solar system sent its help. About 4 billion years ago, an event known as the Late Heavy Bombardment battered the Earth and the Moon. The orbits of Jupiter and Saturn underwent gravitational adjustments, which destabilized asteroids and icy comets in the far reaches of the solar system. For hundreds of millions of years, these dirty snowballs, rich in frozen water and simple organic compounds, relentlessly rained down on the cooling crust. The combination of water brought by icy comets with the water vapor expelled by volcanoes led the atmosphere to a point of extreme saturation. As the Earth's crust finally cooled below the boiling point of water, the sky collapsed. The first raindrops began to fall. When they touched the superheated rocks, they immediately turned into hissing steam. But the rain did not stop. The longest storm in history had begun. It was an uninterrupted cosmic deluge. It rained incessantly for millions of years. The water flowed down the volcanic slopes and began to fill the vast craters and depressions created by asteroid impacts. The water further cooled the crust, allowing the rain to accumulate instead of evaporating. The deafening sound of water hitting the barren rock was the only music on Earth for eons. Fire was being defeated by ice and water. When the great storm finally ceased and the thick clouds began to part, the Earth had transformed. It was no longer a ball of black and red magma. It had become a world of deep waters and emeralds. Global and shallow oceans covered almost the entire surface, rich in dissolved iron that gave the water a dark green hue. But these seas were violent. The moon, still very close, pulled monstrous tides hundreds of meters high, mercilessly sweeping away the newly born small volcanic islands. The surface of the planet was lethal, bathed in ultraviolet radiation from the sun, as there was no ozone layer. But under the crushing waves, in the deep darkness where sunlight never reached, the ocean floor was alive with geothermal activity. Cracks in the oceanic crust expelled boiling, mineral-rich fluids directly from the Earth's mantle. These were the hydrothermal vents, the underwater volcanic chimneys that would become the true womb of life. In those abyssal vents, a silent miracle was being prepared. The chemistry of seawater mixed with volcanic heat, hydrogen, sulfur, and carbon compounds that meteorites had brought from deep space. Far from the sterilization of solar radiation, the overwhelming pressure and geothermal heat began to force these simple molecules to join together in increasingly long and intricate chains. Inorganic matter was flirting with biology. Scientists believe that, in the alkaline micropores of these underwater rocks, RNA molecules began to form in a rudimentary way. Chemical chains that, by sheer chance of the laws of thermodynamics, gained the impossible ability to replicate themselves. They were not animals, nor were they even complete cells. They were merely isolated, self-replicating molecules within tiny lipid bubbles. blindly struggling for chemical survival in a toxic ocean. Billions of failed reactions occurred, until a specific arrangement worked perfectly. A primitive genetic code was securely encapsulated within a protective membrane, capable of metabolizing energy from its environment without needing sunlight. Approximately 3.8 billion years ago, the first living prokaryotic cell emerged, the last universal common ancestor. Biology had officially entered the cosmic stage. These primitive bacteria were the only tenants on the entire planet. Extremophiles that lived in the dark, breathing sulfur and iron compounds to survive. For almost 2 billion years, Earth seemed biologically stagnant. If aliens had visited our planet during that time, they would have seen only a vast and desolate green ocean under a cloudy sky, with no obvious indication that the planet harbored vibrant and resilient life at its depths. But evolution is nature's most persistent engine. The chemical food in volcanic depths was limited. Some of these bacteria began to float closer to the lethal surface, where sunlight pierced the water. Most died fried by ultraviolet radiation. But randomly, a brilliant mutation occurred. Some bacteria developed pigments capable of absorbing the dangerous solar energy without dying. They discovered photosynthesis. Cyanobacteria, the technological vanguard of ancient life, learned to use abundant sunlight and carbon dioxide to produce their own food, releasing a residual gas in the process. These bacteria spread like wildfire in the shallow, sunlit waters. They formed massive colonies, muddy reefs called stromatolites, the fossilized remains of which we can still touch today on the remote coasts of Australia. But its greatest innovation was an act of planetary pollution. The residual gas that cyanobacteria tirelessly released through photosynthesis was lethal to almost all other forms of life at the time. It was highly reactive, corrosive, and destroyed the cell membranes of older bacteria. This invisible and deadly gas was oxygen. The success of cyanobacteria condemned the rest of the world to a chemical holocaust. The newly generated free oxygen first bonded with the iron dissolved in the green oceans. The iron oxidized, turned to rust, and precipitated to the ocean floor, forming the immense mineral deposits from which we extract our modern steel. When all the iron in the ocean had rusted and the water became clear and blue, the oxygen finally escaped into the atmosphere in alarming amounts. The skies began to change from alien red to familiar blue. The Great Oxygenation Event occurred, the first mass extinction in Earth's history. Oxygen-intolerant bacteria died by the trillions, retreating to the dark, airless recesses of the planet, where they remain to this day. The atmosphere was permanently altered. The poisonous stage was cleared. Life had just forged a lethal atmosphere that would become the rocket fuel for all the more complex, fast, and hungry creatures. Biology was ready to explode into unimaginable colors and shapes. The oxygen revolution nearly extinguished life, but created the foundations for us. The oxygen released by cyanobacteria rose to the top of the stratosphere. There, bombarded by relentless solar radiation, it became ozone. A thin yet formidable layer of gas formed around the globe, acting as an invisible shield blocking the lethal ultraviolet rays. For the first time in the history of the Earth, the shallow waters and the edges of the continents were no longer zones of death due to radiation. The abundance of oxygen in the water forced a radical adaptation. Simple cells had to learn to cope with this corrosive gas or die. In a rare event of endosymbiosis, a larger bacterium engulfed a smaller one that was specialized in using oxygen to generate energy. But instead of digesting it, they formed a partnership. The engulfed cell became the mitochondrion, the powerhouse of the cell. The eukaryotic cell was born, equipped with a nucleus, and with an exponentially greater energy capacity. With the energy provided by the mitochondria, eukaryotic cells no longer needed to exist as solitary hermits. They began to group together, communicate chemically, and divide tasks. Some became responsible for locomotion, others for digestion, This selfless cooperation was the beginning of multicellular life. What was once microscopic was now starting to be visible to the naked eye. The oceans became soft gardens of alien organisms and immobile beings anchored to the bottom. This was a peaceful and slow era, known as the Ediacaran period, dominated by creatures that resembled soft leaves, discs, and gelatinous tubes floating on the ocean floor. They had no mouth, no eyes, and absorbed nutrients directly from the water. It was the biological Garden of Eden on Earth. No one ate anyone. There were no predators or prey. Life was a peaceful experience of organic fronds gently cradled by the currents of a spine-free sea. But the biological paradise violently collapsed 540 million years ago in the so-called Cambrian explosion. Evolution hit the accelerator. The need for energy pushed some creatures to stop merely filtering water and start devouring their neighbors. With the first animal biting another, the most formidable evolutionary arms race on the planet began. Biology became a war for survival at any cost. To survive predators, prey developed armor, forming the first hard exoskeletons, impenetrable limestone shells, and protective spines. The oceans were taken over by arthropods, the ancestors of modern insects and crabs. The most famous of them was the trilobite, with its heavy, segmented armor, which ruled the sea floors and swept the ancient, defenseless Ediacaran communities into the cold pages of extinction. To break through these formidable armors, predators evolved terrible weapons: crushing claws, serrated jaws, and, most crucial of all, vision. The development of the first complex eyes changed the game irreversibly. Monstrous creatures like the Anomalocaris, a 1-meter-long hunter with spiny appendages and formidable compound eyes, patrolled the waters as primitive superpredators, establishing the brutal law of the food chain where sight was the key to killing or fleeing. In the midst of these monsters with armored exoskeletons, there was an insignificant creature, no bigger than a thumb, called Pikaia. It was vulnerable, without armor, resembling a translucent, muscular ribbon, but it possessed a vital internal innovation: a flexible, cartilaginous rod that ran throughout its body, allowing for much faster zigzag swimming. This was the notochord, the original biological design from which all backbones, fish, and, consequently, ourselves would emerge. Over millions of years, the descendants of Pikaia hardened this internal structure with calcium, creating the first real skeleton. We had entered the age of fish. They dominated swimming, developing powerful fins and a movable jaw, a definitive weapon to grab and shred prey without losing mobility. The Devonian oceans were filled with ancient sharks and giant placoderm fish, with bony armor surrounding their monstrous heads. Until now, the continents, large blocks of inert rock floating on the Earth's mantle, remained desolate and brown. No animal sounds had echoed on solid ground. It was a landscape as barren as the surface of Mars today. But life in the shallow oceans was becoming claustrophobic and too dangerous. The green algae, seeking refuge and more abundant sunlight, began to attach themselves to the wet stones around the banks and rivers. The great invasion of the land had begun. Over millions of years of evolution, these algae transformed into mosses and then into the first vascular plants, developing rough roots to anchor themselves to the rock and structural tissue to stand against the relentless gravity. They spread a continuous green mantle over the barren rock. As the plants breathed furiously, they pumped even more oxygen into the atmosphere, altering global chemistry once again and creating the humid environment for pioneering animals. Where plants go, opportunists follow. The first animals to leave the safety of water and face the dry air were not us, the vertebrates, but rather the arthropods. Ancient sea scorpions and primitive millipedes crawled onto the ancient shores. They already had hard armors that prevented them from drying under the scorching sun. The untouched banquet of the new terrestrial plants offered a limitless refuge against the predatory fish devouring the ancient oceans. The competition in the waters remained deadly. Some fish, with fleshy, lobed fins, which lived in shallow swamps subject to seasonal drying and low-oxygen water, developed primitive lungs to gulp air directly from the surface. When the water receded, they used their robust fins not to swim, but to push their heavy bodies through the mud to the next available puddle. They were stepping on firm ground. Those clumsy fish that walked became the first amphibians. We had conquered the beach. The Carboniferous period brought vast and dense, swampy forests that covered entire continents. Life exploded. The oxygen level in the atmosphere rose incredibly. This thick oxygen allowed insects breathing through their skin to grow to monstrous sizes. Dragonflies the size of eagles crossed the heavy skies, while giant centipedes hunted in the damp vegetation. The amphibians dominated, but they had a fatal design flaw. They were still enslaved by water. They needed to return to the swamps to lay their soft, moist eggs, or they would dry out in the relentless sun. But evolution solved this with the invention of the amniotic egg, a time capsule shielded, a hard leather shell that kept a private ocean inside it. The first reptiles were born. Free from the constant dominance of water, they marched into the scorching and arid interior of the supercontinents that were merging. They developed thick, scaly skins that retained all the water in their bodies. These ancestors began to diversify radically. Some developed large sails on their backs to regulate heat, becoming the fierce synapsids, the saber-toothed predators and very distant ancestors of mammals. But the end of the Permian period, 252 million years ago, would prove that life on Earth is always on the brink of collapse. The greatest disaster in planetary history was about to tear the globe apart. In what is now Siberia, the Earth's crust broke apart massively, unleashing relentless volcanic eruptions, a silent march of fiery destruction. The true killer was not the red lava, but the invisible gases. The carbon dioxide and methane expelled by the global fracture triggered a catastrophic greenhouse effect. The temperature of the oceans rose brutally to 40 degrees, cooking the living creatures. The water stagnated and became a toxic brew. This event is painfully known as the Great Dying. It was the moment when complex life came closest to being permanently eradicated from the known universe. 96% of all marine species and more than 70% of all terrestrial vertebrate animals choked and died, suffocated, or starved. The planet became silent and scorched. But life, clinging to the cool and forgotten refuges, did not give up on the land. After several million years of terrible desolation, ecosystems began to slowly rebuild a new foundation in the Triassic period. A group of upright, light, and highly agile creatures emerged, hunting anything that moved in the ashes of calamity. They grew, diversified, and multiplied, replacing the ancient pre-Permian rulers. They inherited a land where the continents had merged into a single, brutally dry supercontinent, Pangaea. The age of dinosaurs dawned majestically. They developed fast metabolisms and unmatched predatory aggression. During the long 160 million years that followed, they would unquestionably rule the land, the shallow sea, and the skies. From the formidable titanic herbivorous quadrupeds to the deadly wonders of aggressive biomechanical creatures like the Tyrannosaurus rex. For the biosphere, dinosaurs seem to be the definitive biological winners. And our ancestors? They also survived the Great Death. However, in the shadow of the new scaly giants, they could not compete in the light of day. The first true mammals were marginalized and reduced to the size of tiny, frightened shrews. We were forced to become nocturnal creatures of the shadows. To survive, we developed thick fur, sophisticated ears, and nutritious milk. During endless eras that lasted longer than any human empire dares to imagine, it seemed that this nightly arrangement would last forever. The dinosaurs ruled the golden hours, illuminated by the warm sun, and the tiny mammals frantically rummaged through the damp darkness, accepting their status as supporting characters. The biological hierarchy was permanently locked at the base of strength, until random luck, coming from the cold and chaotic depths of outer space, sent a formidable gravitational course correction. A destabilized rock in the dark void found its way into Earth's orbit, carrying with it the immediate end of a proud dynasty and the bloody beginning of the next revolution. Only the final chapters were missing. The reign of the mammals was about to begin with a devastating flash. 66 million years ago, a 10-kilometer-wide rock tore through the atmosphere over the Yucatan Peninsula in Mexico. The impact released the energy of billions of simultaneous atomic bombs. A scorching heat wave swept across the continents, igniting entire forests within minutes. Tsunamis hundreds of meters high swept the globe's coastlines. But the true catastrophe came in the following days. Trillions of tons of dust, vaporized rock, and soot were thrown into the stratosphere, blocking sunlight. The Earth plunged into an impact winter that lasted for years. The plants, without sunlight, died. The giant herbivores starved to death. And soon after, the formidable predators that fed on them also perished. 75% of all species were swept from existence. The reign of 160 million years of non-avian dinosaurs ended in darkness, not due to biological failure, but due to sheer cosmic bad luck. Silence once again reigned on the wounded planet, but in the underground, where the temperature was stable and the dead seeds and roots provided sustenance, our small ancestors survived. The first mammals, accustomed to living in the shadows and needing little food, emerged from the ashes when the smoke finally cleared. They found an empty world. The great predators had disappeared. The ecological niches were wide open. The tragedy of the dinosaurs was the greatest opportunity in evolutionary history for our lineage. Evolution hit the accelerator again. In just a few million years, those small, nocturnal beings aggressively diversified. They grew in size, lost their fear of the day, and occupied the plains, the seas, and the trees. The ancestors of horses, whales, and felines emerged. Warm blood and adaptable intelligence allowed mammals to conquer the newly cleared globe. In dense tropical forests, a specific group of mammals sought refuge in the treetops: primitive primates. To survive in this complex three-dimensional environment, they developed hands with opposable thumbs, perfect for grasping branches. Their eyes moved to the front of their faces, allowing for binocular vision and depth perception, essential for calculating leaps of dozens of meters from the ground. We were building the physical hardware for intelligence. We moved back to about 6 to 8 million years ago. The global climate changed again, becoming cooler and drier. The dense tropical forests of East Africa began to shrink, replaced by vast and dangerous savannas of tall grass. For primates accustomed to the safety of the trees, it was an existential crisis. Some retreated with the forest. Others, however, were forced to descend to the ground in search of food. On the tall grass of the savanna, moving on all fours was a terrible disadvantage. It was impossible to see the large felines approaching. Those who could temporarily balance on two hind legs survived longer. Millennium after millennium, the pelvis and spine adapted. Complete bipedalism was born with the Australopithecus. By standing upright, we lost speed, but we gained our greatest asset. Our hands became permanently free. Free hands could carry food, hold puppies, and, most revolutionary of all, manipulate the environment. About 2.5 million years ago, Homo habilis began deliberately chipping stones to create sharp edges. For the first time in the history of life, an animal did not wait for evolution to change its body to adapt to the environment. It used its mind to create tools that changed the environment around it. The following invention changed our biology. Homo erectus tamed the most feared beast of nature: fire. Fire provided warmth against the glacial cold and light in the darkness, warding off predators. But its greatest contribution was cooking. Cooking meat and vegetables pre-digested food, releasing massive calories with much less chewing effort. This excess energy was channeled directly to the hungriest organ in our body, the brain, which doubled in size. With larger brains and efficient tools, different human species began to migrate out of Africa, facing the relentless ice ages of Europe and Asia. Neanderthals became masters of survival in the ice, hunting mammoths with sturdy spears. But they were not alone. A new lineage was being forged on the African continent, a lineage with an invisible yet unbeatable advantage. About 300,000 years ago, Homo sapiens emerged. We were not the strongest or the fastest, and our senses were mediocre. But our larynx descended, allowing for a complex range of sounds. Complex language was born, not just to alert about lions, but to gossip, teach, and most importantly, to talk about things that did not physically exist: spirits, myths, rules. This cognitive revolution allowed thousands of humans to cooperate flexibly. About 10,000 years ago, the glaciers receded. In a milder climate, humanity made its riskiest bet: the agricultural revolution. Instead of wandering in search of game, we tamed wheat and animals. We settled in one place. Food became abundant, the population exploded, but the cost was high. Diseases arose from living in crowded conditions, social inequality, and the hard, repetitive work of the fields. The hunter-gatherer became the peasant. To manage grain stocks and large populations, human memory was no longer sufficient. In the valleys of Mesopotamia, Egypt, and China, we invented symbols on clay and papyrus. Writing. With it, ideas gained immortality. Cities, empires, laws, kings, and institutional gods emerged. Recorded history, with all its bloodshed and architectural achievements, began its accelerated march. For millennia, we believed ourselves to be the center of the universe, an immutable divine creation. But in the 16th century, the scientific revolution shattered this comforting illusion. Men like Copernicus, Galileo, and Newton turned glass tubes to the sky and discovered that the Earth was not the center of anything. We were merely a planet orbiting a common star. We exchanged mythical arrogance for the humility of mathematical facts. Science-generated technology. The Industrial Revolution replaced human and animal muscles with the energy of coal and steam. Productivity skyrocketed to the stratosphere. In less than 3 centuries, we illuminated the nights with electricity, eradicated millennia-old diseases with antibiotics, and connected the globe with trains, ships, and telegraph cables. The human species became a geological force capable of altering the chemistry of the entire planet. In the 20th century, we uncovered the secrets of the Big Bang itself. We split the atom. We mastered Einstein's equation that dictated the creation of matter, but we first used it to build weapons capable of annihilating our own civilization in minutes. The power that forges the stars was now in the hands of emotionally unstable bipedal apes. We survived the Cold War not through wisdom, but through terrifying luck. But we also used that same physics for our moment of greatest pride. In 1969, just 66 years after the first fragile airplane took to the skies, a colossal rocket spewed fire and broke the gravity that had held us for 4 billion years. Humanity set foot on the moon. For the first time since the dawn of biology, life left its home planet and touched the inert dust of another world. Today we live in the information age. An invisible network connects almost all 8 billion human brains instantly. We have mapped our own genome, understanding the source code of life. We have created artificial intelligence, teaching silicon and electricity to think, paint, and solve problems. We are, possibly, building our next evolutionary leap not in biology, but in technology. But our resounding success comes at a terrible price. The carbon dioxide that our machines exhale is warming the planet at a rate that mimics the great extinctions of the past. The oceans are acidifying, forests are burning, and ancient ice is melting. We have become so powerful that we are now the asteroid itself. Our survival in the coming decades will depend on our ability to cooperate not as tribes anymore, but as a single, global species. Carl Sagan warned us when he showed the picture of the pale blue dot. There is no indication that help will come from elsewhere to save us from ourselves. In the relentless and cold vastness of the universe, our world is the only known lifeboat. Our arrogance, our empires, and our wars are fought in a cosmic grain of dust suspended in a sunbeam. If we want consciousness to survive in the long term, we will have to leave the cradle. We are already looking at Mars and beyond. In the future, humanity may become a multi-planetary species, terraforming dead worlds and seeding life throughout the galaxy. Taking earthly biology to the stars from where its atoms originally came, we are the way the universe decided to colonize itself, because the Earth is not eternal. In about 5 billion years, our sun will exhaust its hydrogen. It will swell, becoming a monstrous red giant. The oceans of the Earth will boil and evaporate into space. The mountains will melt. The sun will swallow the entire Earth, obliterating any trace that we were ever here. If humanity has not left by then, our story will end in the same fire from which it began. And the universe? Trillions of years in the future, the last star will extinguish. The galaxies will dissolve into darkness. The black holes will evaporate through Hawking radiation until nothing remains. Entropy will prevail. The universe will reach thermal death, a state of eternal cold and darkness where no energy can be exchanged and no life can exist. The clock that started at the Big Bang will finally stop forever. Does this make our existence meaningless? On the contrary, the universe spent billions of years being nothing but dead rocks, boiling gas, and brutal collisions. But here, on this tiny blue dot, dead matter organized itself into something incredibly rare. Cells became hearts, brains, and eyes. For the first time in 13.8 billion years, the universe gained the ability to look back, to calculate its own age, to compose music, and to love. We are not fallen observers in the universe. We are the universe, experiencing itself. The time we have in the light is short and precious, a miracle of mathematical improbabilities. It is up to us to decide how we will use this ephemeral awareness before the darkness returns. Thank you very much for joining us on this journey through space and time. Subscribe to the channel so we can continue to explore the mysteries of our cosmic existence. Follow us.